Okay, so so this is 9.3 continued, and we were working with volumes, right? And so, we had been doing before, oops, one more page. Okay, so last class we talked about the disk method, and we found how do you find the volume when you have solid disks. And so today we're going to talk about what's called the washer method. And so the washer method is used when we're trying to find the volumes of things that have basically a hole in them. Or some kind of opening. The hole doesn't have to go all the way through. And so I'm going to show you here what I mean. So, for example, find the volume of the solid formed by revolving the region bounded by y equals the square root of x and y equals x cubed about the x-axis. So if I think about drawing that area, right, so y equals x squared, or y equals the square root of x looks like that. So this is y equals square root of x. Y equals x cubed looks like that. And so we're talking about this area here, right? So remember last time I shaded the area we were talking about. And then we're going to rotate that about the x-axis. So I'm going to make that mirror image over here. And then if we think about connecting that up. So basically the shape that that's making, if you think about it, that shaded part is going all the way around. So think of it, it's almost like a cereal bowl, right? So if you had a cereal bowl, except that usually in a cereal bowl, the inside part looks like this. In this cereal bowl, it's a little weird. The inside part kind of like curves in. But does that kind of make sense what I mean, where there's like a hollow or a hole type thing? Because it's like, you know, in the bowl, the middle of your bowl is hollowed out. Questions? No. Okay, so in this shape, when you go to, if you were to, kind of like last time how we made the discs, this time the disc, they wouldn't be a solid disc. It would actually be, if I think about sticking one in here, right, I have that outer part, and then I would have this inner part that's hollowed out. So that's why it's called the washer method, is because it looks like a bunch of washers, right? So you can kind of see where that hole would be in the center. So if I want to find the area of a washer, how would I find the area of a washer? How would I find the area of something that has like an outer radius and an inner radius? And you're just talking about all this space in between them. Yeah, so you could find the area of the bigger circle and then subtract off the area of the little circle. So remember when we did the disk method last time, the formula we were using was 2 pi, or was not 2 pi. Remember it was pi, the integral of, we called it whatever the radius was, squared d something, right? That was kind of the generic form that we used last time. So this time we're just going to tweak this a little bit. So we're going to find the outer area and then subtract off the inner area. We can actually do that all in one step by saying when we're dealing with washers, the volume is going to be pi times the integral of the outer radius squared minus the inner radius squared d whatever. And just like before, if I'm rotating around the x-axis, we're going to use a dx. If I'm rotating around the y-axis, we're going to use a dy. So, questions? No. Okay, so if I go to plug in here, so we're going to have pi times the integral of something squared minus something else squared. And then I said we're rotating around the x, so it's going to be a dx. My outer radius, right? Where is the outer radius sitting in this picture? So remember the outer radius. Yeah, the outer radius is on that square root of x. It's going from the center all the way up to this top curve here. And that is the curve, the square root of x, right? So it's the square root of x squared. The inner radius is in here. Where's that inner radius sitting on? I probably should use a color that was different than green, because that's not really easy to see. But yeah, the inner radius is sitting on the x cubed. And then I have to figure out where I need to integrate from where to where. So how am I going to figure that out? What do I have to do to find my limits of integration on this problem? Yeah, so it's going to be from 0, that's where they're starting, that's where they cross, to wherever else they intersect. So really what I'm trying to do is I'm trying to solve, let me pull this up here so I don't accidentally hit stuff. I'm trying to solve when is x cubed equal to the square root of x, right? So you could square both sides, right, to figure this out. So if I squared both sides, I'm going to have x to the 6th equals x, right? If I square this side and I square this side. And then if I pull these over, I'd have x to the 6th minus x equals 0. So we're going to have x times x to the 5th minus 1 equals 0. So x is going to be equal to 0. And that makes sense, right? We can see that they cross at 0. And then the other one is going to be when x to the 5th minus 1 equals 0. So that's going to be when x to the 5th equals a positive 1, or when x is equal to the 5th root of 1, which is just 1. So the other place is going to be at 1. So we're going to integrate this from 0 to 1. So questions on the setup before we actually work out the problem? No? Okay, so I'm going to do this then. So I have pi. I'm going to do this algebra first. So the square root. Okay, so on the actual picture, so on which part of the picture? Like how I got the picture in the beginning, like the radius part of the picture. Okay. Yeah, so, the bottom part. So, I don't have to worry. The bottom part is just the reflection of the original part, right? So, I only have to worry, and this is one of the reasons why I shade the part. I only have to worry about the shaded part. I'm only interested in trying to find the radius of the shaded part. So, if you think about the washer, right? This basically, I have sitting here, right? My washer is sitting here, and at the top, my washer is sitting on the curve. This is that curve, square root of x. And then that other curve that's kind of coming through here, that's that x cubed. So my outer radius went from here all the way up to that square root of x. And then my inner radius, let me find a better color than that green. because it's kind of dark green. What about if we try a little bit of a lighter green? My inner radius goes from here up just to this part there. So that's why my outer radius starts at 0 and goes up to square root of x, and then my inner radius starts at 0 and goes up to x cubed. Does that help on the picture? No problem. Other questions? Okay, so we just need to square out these functions here. So I have 0 to 1. Square root of x squared is just x. And then x cubed squared is minus x to the 6th. So I have x minus x to the 6th dx. And now I just want to integrate these. So I have pi, and then what's the integral of x? Yep, x squared over 2 minus, what's the integral of x to the 6th? Yep, x is 7th over 7. And then I'm evaluating that from 0 to 1. So we're going to have pi times, if I put 1 in, I get 1 squared over 2 minus 1 to the 7th over 7 minus, if I put in 0, 0 squared over 2 minus 0 to the 7th over 7. Okay. So we've got pi times 1/2 minus 1/7. And so 1/2 minus 1/7 is 5 over 14. So this is 5 pi over 14, right? If you made a common denominator. Questions? No. All right. Does anybody need me to wait before I go to the next page? No. So find the volume of the solid formed by revolving the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. Okay, so the first thing I need to do is kind of draw what we're dealing with here. And I'm going to make mine pretty big here. So here's 1. So if we're talking about y equals x squared plus 1, we've got a parabola, right? That's raised up 1. Y equals 0. So y equals 0 is here, the x-axis. X equals 0 is here at the, I should have said, oh no, I said x equals 1. Okay. Yeah, x equals 0 is here. And then x equals 1 is here. right? So this is 1 on the x. So we're talking about taking this shape. And remember, this is the curve y equals x squared plus 1. So when x is 1, this point here, I just have to plug it in. So it would be 1 squared plus 1. So this is the point 1 comma 2. That might turn out to be needing to be helpful for us. So does anybody have questions on how I got that first area? So that's the area. I haven't spun it yet, but that's the area we're dealing with. No? Okay, and then we're going to rotate this around the y-axis. So I kind of already sort of have a mirror image going on here. And then I kind of usually like to put a round thing at both kind of ends. And so this is an interesting shape, right? It's kind of like there's a bowl, but then there's a chunk of solid stuff underneath the bowl, right? So it's like I have a cylinder, okay? And so think of like a candle, like think of like a round cylinder candle. And then I've carved out from the top part of the candle, like a bowl shape inside. Does that kind of make sense as to what's going on here? How do I know it meets at y equals 2? Okay, so the reason I know it meets at y equals 2 is because this curve here, I know is y equals x squared plus 1. And so x is 1, so if I plugged 1 in here, I got 1 squared plus 1, and 1 squared plus 1 is 2. So that's how come I know that that point there is 2. Does that help? No problem. Other questions? Okay, so it is the washer method and it isn't the washer method. It's actually, this one, we actually have to use both the disc method and the washer method. And so the reason why is because if you think about it, if I'm up here, right, if I'm up in this area, then it's definitely a washer, right? So sitting in there, I definitely have that washer. But if I come down here, it's solid. So down here, I have to deal with a disc, right? So down here, I have to deal with a disc. Up here, I have to deal with a washer. So I actually have to break this problem into 2 pieces. And we're going to break it right here, right? That's where everything underneath that blue line is solid. So underneath that blue line, we're just going to use the disc method. And then above the blue line, we're going to have to use the washer method. Does that make sense? So, unfortunately, when you're dealing with the disc and the washer method, you're kind of a little limited, and you have to, you can only use the washer, the disc part when you have solid stuff, and you can only use the washer when you have the hole. And in this problem, I happen to have the solid part and the hole part. What we're going to learn next, in 9.3 part 2, I'm calling it, is we're going to learn a different method where you wouldn't actually have to do this problem 2 ways. You could actually just do this problem in one swoop. But we're not there yet. So right now we have to worry about the disc part. So the solid part. So I have to worry about the solid part and then the bowl part. So there's basically a solid cylinder in the bottom, and then I'm going to have to find the volume of that, and then I'm going to have to add that to the bowl part top. Right, so this is going to require us to set up 2 different integrals. So it's a good review of the disc method. So the bottom part. So let's start with the bottom part. The volume for the bottom part is going to be pi times some integral. I revolved around the y-axis, so it's going to be a dy, and it's got the radius squared. So the radius squared dy. And if I think about the radius starts here in the middle and it goes all the way out to the edge. So how big is that radius? Yeah, that radius is a 1. So it's a little weird. It's always a 1 in this case, right? It's never moving in. It's just I have this cylinder that happens, it's solid chunk, the solid cylinder chunk, where the radius happens to be 1. So we're just talking about 1 squared dy. And then we're adding up those disks. Where do I start adding up those disks? They start at what point? Like, where's the bottom of that solid? Yeah, the bottom is at 0. And then I keep adding them up until I get to what y value? Yeah, till I get to 1. So this is actually a pretty nice integral, right? So this first part here is going to be pi times the integral from 0 to 1 of 1 dy. And what's the integral of 1? Yeah, y. So this is going to be pi times y evaluated from 0 to 1. So we're talking about pi times 1 minus 0. So this first part just gives me pi. So that wasn't too bad. For the second part, right, so we'll just bring the plus sign all the way down here. So plus. So for the second part, the volume is going to be pi times the integral, but this time we have an outer radius squared minus an inner radius squared, and then we're doing dy, right? Again, we're still doing dy. So my outer radius, right, starts here and goes all the way out to this edge. So the outer radius happens to be what? Oh, damn it. I see. I got very laggy behind you guys. Let me see. If that's still super laggy, I'll just disconnect and like the iPad and then reconnect it. Yeah, so the outer radius is still just 1. So let me see. That was pretty alright. Okay. So the outer radius is 1. And then the inner radius, right? I'm starting here and I'm going up to this point. So what is the inner radius? That's sitting on what curve? Okay, so it's sitting on the x squared plus 1 curve. Exactly. The problem, though, is that I can't write x squared plus 1 in here because, remember, it's a dy. So everything has to be in terms of y. So if I take that curve, y equals x squared plus 1, and I solve it for x, I get y minus 1 equals x squared. So we're going to have plus or minus the square root of y minus 1 is equal to x. And then because we're dealing in that first quadrant where everything's positive, we would be dealing with the positive root. So this is going to be the square root of y minus 1. Quantity squared. And then I'm adding these up from what value to what value. So where are we starting these washers and where are we ending these washers? Yeah, from 1 to 2. So before I actually integrate that, questions on how I got any of that set up for that second integral. Or that second volume, I should say. No. Okay, if you have a question, please definitely ask it. Feel free to throw it into the chat, right? So this is going to be pi times the integral from 1 to 2 of 1 minus the quantity y minus 1 dy, or pi times the integral from 1 to 2 of 1 minus y plus 1 dy, or pi times the integral from 1 to 2 of 2 minus y dy. And then the integral of 2 minus y is going to be what? Or the integral of 2, I should say. Yep. So pi times 2y minus, what's the integral of y? Y. Y squared over 2. And again, evaluated from 1 to 2. So we're going to have pi times, so 2 times 2 minus 2 squared over 2 minus 2 times 1 minus 1 squared over 2. So this is going to be pi times, so I'm going to have 4 minus 2, so that whole first part just ends up being 2. And then I have 2 minus 1/2, so that's going to be a minus, then 3/2. And so 2 minus 3/2 would be 1/2. So I end up with pi from this first part plus pi times 1/2, or if I put them all together, maybe I should probably do it underneath, we end up with 3 pi over 2. Questions? Y is which part 3/2? The very end or the part in the bowl part integral? The very end. Because I have one whole one here, so I have 1 pi plus a 1/2 pi. So 1 plus a 1/2 is 3/2. Does that make sense? Oh, okay. So the 2 minus 3/2 part, right? So remember, if you made this a common denominator, this would be over 1. So if you multiply the top and bottom by 2, you would have 2. Oh, you mean how did I get 3/2 there? Like, wait a minute. I think I just did the wrong part. How did I get that 3/2? So that 3/2 came from here. This is 2 minus 1/2. So this would be 2 over 1. And then multiply top and bottom by 2. So you would have 4 over 2 minus 1 over 2, which is 3 over 2. So that's how I did that. So then I have 2 minus 3 over 2. And then 2 minus 3/2 is 1/2, right? Because 2 is 4/2. No problem. Other questions? That's okay. So discs really isn't that different than washers. I mean, washers really isn't that different than discs, right? The only difference in washers is you have the outer radius and you have an inner radius. That's the only difference. And so you just have to kind of figure out what's the outer radius, what's the inner radius. So those two methods are kind of the same, right? Essentially, we're putting a circle in there. The next method, so this is essentially, the next part that I'm going to do here is what I'm going to call section 9.3 part 2, So our textbook, most textbooks don't put all of the volumes in one chapter. Usually they put discs and washers together, and then they do, or section, and then they do a second section where they do volumes. And so that's kind of how I had the homework structured, and I didn't realize that our book at first stuck it all in one section. So that's why I just called it 9.3 part 2, since I'd already made the 9.3 homework. This is 9.3 part 2, and this is volumes by cylindrical shells. Okay, so we're still going to take it, we're still going to take a region, we're still going to rotate it just like we have been doing for the washers and the discs. The difference here is the screen frozen? Oh, all right, let me go back to recording. Okay, so as I was saying, so in the last section, we built up our volume by thinking of it as like I have these round discs, and maybe the round discs are solid or the round discs are hollow. There's another way that you can build up shapes. So for instance, if we take that last shape that I had, right? So, I'm just going to kind of on this page show you like what's going on with volumes. So if you think about that last, if you think about that last shape we had, and I'm going to draw it really big here. The last shape we had was kind of this type shape, right? And then I rotated it around. So I made that mirror image on this side, and then we had this rotated around this way. So one of the ways that I could build up this shape is by thinking of taking like very tiny little cylinders. So I could start in the very middle here with one tiny little cylinder, right? And then I could keep kind of putting bigger and bigger cylinders around this. So if you think about it, if I started taking cylinders that were like the width of a piece of paper, and I kept wrapping them around, right? Eventually I would begin to build out my shape. So maybe then I'm out here and so I'm not drawing obviously every single cylinder, but you can see that basically we can build the shape from a bunch of cylinders. So, and then as I move up, I've got even more cylinders, right, coming, and then even up here, right, here's another cylinder. So you can think of your shapes as being made up of a bunch of these cylinders, right, until I finally got out to that very last cylinder that we had, right? So maybe I'll draw one more here. So basically, if you're bored, right, during COVID here, you're stuck at home and you're bored, you can start making shapes by taking pieces of paper and just rolling them and taping them up into a cylinder, and then putting another piece of paper, maybe it's a little tiny bit higher, and then another one that's a little tiny bit higher, and another one that's a little tiny bit higher. So you can kind of like, I don't know if anyone's ever done this, but like when I'm at a restaurant, right? Which haven't been in a restaurant in a long time, but if I'm in a restaurant and, anybody, you know how like sometimes at restaurants, the napkins are full of, like the napkin and the silverware is like, there's a piece of paper that goes around them to hold it together, right? So I personally, every time I'm at a restaurant and my silverware and napkin are wrapped with one of those strips of paper, I actually usually tend to take the strip of paper and just like roll it so it's like a tight little coil, right? But then I kind of like it because then I can like push my finger on the top part and push it down and stuff like that. And so that's essentially sort of what's happening here, right? Like you can think about it like, oh, I can make a little dip shape if I pushed all those cylinders down and had them of different heights. You could think about it like so when I learned calculus way back lots of years ago now, so more than 20 years ago is when I learned calculus, which makes me very old at this point of my life. But my calculus teacher brought in a bunch of cans. So he brought in like tuna fish cans and soup cans, and all different size cans where he had cut the top and the bottom off, and then he stacked them inside of each other to make shapes, right? So, do you kind of see what I mean about how you have all these little cylinders and you're like stacking them inside of each other to make these shapes? Okay. Yeah, like a toilet paper roll. So you could take a toilet paper roll and then you could take like, bigger toilet paper rolls, right? All toilet paper rolls are usually pretty standard to fit on a thing. But yeah, essentially we're taking toilet paper type rolls. So we have these hollow cylinders, right? So if you take, and I have a piece of paper here. Okay, so if I take, so here's my piece of paper, right, and it makes a cylinder. If I unroll my cylinder, it's really just a rectangle, right? So cylinders are really just made from a rectangle, especially cylinders that don't have a top or a bottom. So to find the area, so whereas before we found the area of the disc or the washer, and then we added them up using the integral, here in the cylinder method, we are going to find the area of the cylinder and then add up all of our cylinders using an integral. So our cylinder becomes a rectangle, right? So on my cylinder, so if you think about how do I find the area of the rectangle, of a rectangle? Yeah, length times width, right? So, or width times height. Yeah, either way. So if we think of this as being the height, so generally we usually say length times width. I'm going to say height just because I want to relate it back to the cylinder. So if you think about, yeah, see, it paused for me. I don't know why it's, let me see, because I just have the little up and down line where I wrote actually on my paper an H. Oh, see, there comes the H. Can everybody see the little H now? Yeah. Yeah, I think this is my issue. Since I just got a thing that was like, your internet is unstable. So we're going to go with it. We're going to see how well this goes. Yeah. So we'll see. Hopefully, I'm hoping it probably caught up. We'll see how it goes. So, but if I'm writing, you guys can't see it, definitely let me know. Okay, so the height of the rectangle is the same as the height of the cylinder. And then the length of the rectangle, so when you think about it, if I take my rectangular piece of paper here and I roll it into a cylinder, the length of the rectangle, right, becomes the what of the circle for that cylinder, of the circle that's on the end. So the length of the rectangle folds into that cylinder and it becomes what? Yeah, the circumference. Okay, so do we remember, so here I have a radius, r, right? Do we remember how you find the circumference? Yeah, 2 pi r. So this distance on the top of the rectangle here is 2 pi r. And so remember, the integral is going to add up all of our cylinders for us. So volume, another way you can find volume is you can think of it as 2 pi times, we're finding the area of that rectangle. So 2 pi r, so the radius times the height, d something. questions? So that's going to be the volume formula we use. In discs and washers, right, if you rotate around the x-axis, you're using dx. And if you rotate around the y-axis, you're using dy. In shells, it's the other way. So for the shell method, if we rotate around x, rotate about the x-axis, then we're going to use dy. And if we rotate about the y-axis, we're going to then use dx. So shells is like the opposite of what's happening in washers and discs. Okay, so should we try a couple problems? Well, no one's saying yes, but I figure you guys probably would like to see a couple problems before you have to do them on the homework. All right, so find the volume of the solid generated by revolving the region bounded by y equals x minus x cubed and the x-axis in quadrant 1 about the y-axis. Okay, so I'm going to draw the picture first. I'm going to make the picture actually fairly large in this one since it's the first time we're doing it, so that we can kind of see what's really going on. And again, if you are like drawing these, right, this is something where like you might not know what it looks like, what y minus y cubed looks like, and that's okay, right? So again, you could use a graphing calculator to stick it in, you could use Desmos, you could use Wolfram Alpha. There's lots of like internet-based graphing calculators that you can use to basically get the picture of what's going on. So if you were to draw the part of this curve that shows up in the first quadrant, it kind of looks something like that. And so this is that original shape. Again, I always shade the original shape. The reason that I do that is because then mentally I know, okay, this is the original shape. This is where I have to be drawing all of the stuff. This is where I have to be figuring out what the radius is, what the height is, always in the original shape piece. Sometimes when these get a little more complicated, it's hard, like you end up drawing it and you forget you're not in the original shape. It's probably me. Let me disconnect and then reconnect. So, okay, we're rotating this about the y-axis. And so I'm going to draw the mirror image over here. And that's why sometimes I draw the mirror image with a dotted line, just again to remind myself this is not the original shape. And if I think about it, goes around this way and it goes around that way. So it's kind of like, this shape is kind of like as if you like took a mountain, but then you like chopped off the top of the mountain and like made like a concave part into the mountain. So that's kind of what's going on. So it's kind of almost like a donut. It's like a deformed donut where like the donut at the top has the hole, but at the bottom the hole like kind of came together on the donut. Or a bagel, right? That happens sometimes on bagels. Yeah, it would be like a mochi donut. So this is not a good candidate for, because a lot of times when I do these problems, people go, well, couldn't you just use washers, right? Like I could make this a washer problem. So don't copy this down, but I'm gonna draw a washer and then I'm gonna undo it, so that I can show you the problem with if you tried to use washers on this. So if I tried to put a washer on this, right? So here would be my washer. The problem with the washer is that the outer radius is on the function, but our inner radius is actually on the exact same function as well. So you can't use washers if the outer radius and the inner radius are on the same function, because if you do the outer radius squared minus the inner radius squared, you'll just get 0. So that's why in this problem we're going to have to use those shells. So I'm going to get rid of my washer here. And instead of a washer, I'm going to stick in a shell. So I like to put in just some random shell. So I put in a vertical line. I mirror that vertical line on the other side. And then I think about making my shell. And so my volume is going to be 2 pi some integral, which we'll deal with here in a couple minutes, like the limits of integration. We need the radius and then the height. And then since we rotated around the y-axis, it's going to be dx. So let's, so this part here, this is the radius, this first one, and the second one represents the height. So let's talk about the height first, because the height, I think, is the more straightforward one to understand. The height, what is the height sitting on? Like, how would I figure out what the height of that shell is? Okay, so it's the highest point. So think about as I do different shells, right? So like a shell over here, like if I made a blue shell, right? So the bottom of the height touches what value? Like the bottom of all the shells is at 0. The top touches what? Okay, so the blue one, it looks like it kind of touches the vertex, but the pink one's not touching the vertex. So the blue and the pink lines are both the top of the blue and the pink lines, though, here. They're here and here. They're both touching what? I can say that both of these points are touching the blank. So what could I put in for that blank? Yeah, they're both touching the function, right? So all of my heights, no matter where I would draw a cylinder, the height would be touching the function. So the height is going to be the function x minus x cubed, right? So remember, we're trying to put this in generic terms so that it would work for any shell. So it works for the pink shell, it works for the blue shell, right? It works for all the shells. All of the height of a shell is always on the function. Questions about the height? No. Okay, the radius. So the radius of the pink shell starts here at 0 and goes out some value, some number. It goes out to some x value. I just don't know what that is, right? The blue shell does the same thing, starts in the middle, and it goes out to some other x value. I just don't know what that is. So the radius, right? But the radius is I have to do all of the possible radii, right? I'm doing dx. So I have to do all of the possible radius. So the radius is just the different x values. So like I might need to do x equals 0, and I might need to do I would need to do like every single tiny little value in here, right? I would have shells that just go out a tiny little bit, and then I have like a little tiny baby shell here. I would have a bigger shell that goes out a little bit more, right? And it's a bigger shell. So the radius, so the x value is just the radius. In general, not as long as you are rotating, right? So this is kind of like a general tip here. I'm going to write on the side. As long as you are rotating around, like, so when you're rotating around the x or the y axis, right? So if I rotate around the y, my radius is generally going to be x plus or minus something, okay? In this case, it's just x values, but it's possible, like, depending on your problem, you might have to tweak it a tiny little bit. If you rotate around the x-axis, your radius is generally going to be y plus or minus something. So a bunch of the examples we're first going to do, we're just going to deal with the radii being either just plain old x or just plain old y. So we're going to get used to it before we actually start doctoring it up a little bit. So the radius just goes out a little distance, x, and then the height for each of the shells would go onto the function. Questions? No. Okay, and then Sandra said, do you have to find the roots? And so you have to find the roots to determine where the x's start and where the x's stop, right? So we can kind of tell if you look at my shaded region here, right? It started at 0. So hopefully the algebra will bear that out for us. But we're looking for where that function, so where is x minus x cubed actually equal to 0? So that's going to happen when x times 1 minus x squared equals 0. So either x is going to equal 0, or 1 minus x squared equals 0, or 1 equals x squared, or x is equal to plus or minus 1. So remember, we're only dealing with the part in the first quadrant, so that means this point here has to be 1. So we're integrating from 0 to 1. The harder part about these problems is usually setting it up, right? So usually the integral isn't terrible. Some of the shell integrals are a little worse, but generally the integral is not terrible. So if I work this out, this is going to be 2 pi times the integral from 0 to 1 of x squared minus x to the 4th dx. Or 2 pi times x cubed over 3 minus x to the 5th over 5, evaluated from 0 to 1. So 2 pi times, if I plug in 1, I get 1 cubed over 3 minus 1 to the 5th over 5. Minus, if I plug in 0, I get 0 cubed over 3 minus 0 to the 5th over 5. So we end up with 2 pi times 1/3 minus 1/5 or 2 pi times 2 over 15, so 4 pi over 15. Questions? No. And I have more examples, right? So we're going to do, I have 4 more examples we're going to do. So y is at x times the height. So x is the radius. So remember, if I unfold the cylinder, it becomes a rectangle, and we're trying to find the area, and then we're going to add up all the areas to get the volume. So the area of a rectangle is length times width. So in our case, our width is the height, and then the length is the circumference. So it's 2 pi r, and so we need to figure out what the radius of each of these cylinders are. And so if you think about it, the cylinders are varying. I have an infinite number of cylinders going on here, and all the cylinders they're in the radius. You can think about it is like the radius of the cylinder is going along the x-axis. So the radius is just x. Does that help? No problem. Other questions? No. So let's try another one. Find the volume of the solid formed by revolving the region bounded by x equals e to the minus y squared and the y-axis, and the y-axis, the x-axis, y equals 1, about the x-axis. It's pretty terrible grammar I got going on in there, right? I really should say the region bounded by x equals e to the minus y squared, the y-axis, the x-axis, and y equals 1. My and is like in a really terrible spot, but it is what it is. Okay, so e to the minus y squared, if you were to graph this, so if you were to put, so remember the y-axis, like if you want to put all the lines, say, into Desmos, or you want to think about it, remember the y-axis is the line x equals 0, and the x-axis is the line y equals 0, right? So if I do that for these shapes, for these lines here, so our curve, the curve looks something like this. That's the curve y, or not y, x equals e to the minus y squared. The y-axis, right, is x equals 0 here. The x-axis, y equals 0 here. And then I have the line y equals 1. So we're talking about this shape in here. And so we're going to reflect that shape. and we're going to think about rotating it around. And again, you might say, well, this would be a good candidate for discs. And the problem is that if you were to do discs, so all the way up to this point here, you would have one type of disc, right? Your disc would just be, the radius would just be 1, and then here you have to break it up into a second curve to make it a second volume to make the discs, because now the discs are going to be on this curve. So it's not that you can't do this with discs, it's just that it's actually more work to do this with discs than it is to do it with cylinders. So again, if I put in just a random cylinder, right, and so I'm going to kind of mirror that. So there is my random cylinder. So my volume is going to be 2 pi times an integral. So I have to put the radius, the height, and then because I rotated this about the x-axis, whoops, should have drawn my little rotation arrow here, we're going to be doing dy this time. Okay, so my height, this is my height. My height is sitting on what? Yeah, my height is sitting on the curve, so my height is e to the minus y squared. And then my radius this time, right, my radius is going out in the y direction. So my radius is just, I start at 0 and I go out. So my radius is just y. And then in that original shape, where are y's going from? From what to what value? They start at what? Yeah, they start at 0 and they go to 1. So that is the setup for the integral here. Questions? We're going to integrate it, but so if I get rid, I can drop these parentheses, right? So this is really 2 pi, the integral from 0 to 1 of y e to the minus y squared dy. And anybody want to take a guess how we're going to integrate that? Yeah, we're going to have to do a u substitution, right? So again, yeah, so I think an unintended consequence that generally happens in Calc 2 is you learn integration by parts, and then you think everything that it has two things multiplied together is going to be an integration by parts. The thing you want to notice here is, so the power on the power on the exponent here happens to be a squared, and I happen to have a first power here. So when you have stuff that is being multiplied and the powers differ by 1, like in terms of a u substitution, that's a great candidate to do u substitution on. So if I let u be equal to the minus y squared, then du is going to be minus 2y dy. And so I need to put a minus 2 inside here, which means I need to balance by a minus 1/2 out in front. So I've right now got minus pi times the integral of e to the u du. And then you can either change your limits of integration or not change them. I'll change them. So we had x equals 0. Or not x, y equals 0. Help if I write the right thing. So we had y, so when y is equal to 0, u is going to be minus 0 squared, so it's still just going to be 0. And when y was equal to 1, u is going to be minus 1 squared, or negative 1. So we're going to go from 0 to negative 1. And then the integral of e to the u is just e to the u. So I have minus pi e to the u evaluated from 0 to negative 1. So we've got minus pi times, if I drop in the negative 1, I have e to the negative 1 minus e to the 0. So we have minus pi times 1 over e minus 1. And I would just leave the answer like that. Now, you might be going, wait a minute, the answer is negative. Wouldn't negative 1 squared be... okay, negative 1, so you got to be careful about what's happening. The negative is out, the negative here is out in front of the square. So the only thing that's being squared is the y. So this is not, like, if it was like this, like if you were plugging in negative 1. So I should think, you can kind of think of this as this. It's negative 1 squared. So the only thing that's being squared is the 1. So I square the 1, I still get 1, but then I have to make it negative. And so, yeah, you might think, wait a minute, how can volume be negative? The volume's not actually negative, because if you think about it, 1 over e is much smaller than, is a smaller number than 1. So if you do 1 over e minus 1, this inside stuff is going to be negative, and then a negative times a negative actually is a positive. So your answer would be a positive value. Right? If you do these problems and you do end up with a negative value, then you know you did something wrong. Questions? Okay. Find the volume of the solid formed by revolving the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So this problem might sound familiar, and it's because this is the same one we did at the second washer example, right, where we had to split it because the bottom was solid and the top wasn't. So this is that same one. So we've got, here's one. I had that. We had y equals 0, or we had x equals 0, y equals 0, and we had x equals 1. And we said this was the point 1, 2, and this was what we were dealing with, and then we rotated it around. So we had that shape, right? And so before, we had to split it into doing 2 integrals, but the thing about cylinders is cylinders actually lets us do these more complicated shapes without having to split it into multiple pieces. So if I think about putting in a typical cylinder, my cylinder would look like that. And my volume is going to be 2 pi times some integral. We're going to have the radius, the height, and this is going to be dx. So the height, right, in this case is sitting on that equation, x squared plus 1. And the radius, right, my picture is not great looking here, but the radius is just along the x-axis here, so it's just x. And then where are my x values going from? From what to what? Yeah, they're going from 0, and they're ending at 1. So this just becomes 2 pi times the integral from 0 to 1 of x cubed plus x dx. So this is going to be 2 pi times x to the 4th over 4 plus x squared over 2, evaluated from 0 to 1. So we're going to plug in 1. So 2 pi times 1 to the 4th over 4 plus 1 squared over 2 minus 0 to the 4th over 4 plus 0 squared over 2. Or 2 pi times 1/4 plus 1/2. So that's going to be 2 pi times 3/4, or 3 pi over 2, which is exactly what we got before. But this way was a lot more straightforward and easy than what we did on the one where before we had to break it into 2 pieces. We had to re-solve, for the x value. So this makes it a much nicer problem to do. Questions? No. Are they getting a little bit better? Sure. Let me know. Did you have a question on this last slide, or? Oh, no problem. Okay, can I go on to a new slide? Does anybody need to see any of the slides again? No. Okay. Up, record. All right, so find the volume of the solid generated by revolving the figure about the x-axis. Oops, about the y-axis. I'm like, wait a minute. Like, doesn't add up with the picture I had. Okay. So, this is the line y equals 1 minus x over 2, and this is the line y equals x over 2 minus 1. So we're going to take that, we are going to rotate it about the y-axis. So, let me get that. So you can think about it, I kind of have, you know, it's going around this way. I think it kind of looks like a diamond gemstone, right? That's kind of, sort of, it's not exactly what's going on, but it's basically like a, or if you took two tops, like two cones and put them kind of together, that's the shape that we have going on. So it's like the top is a cone and the bottom is a cone. Yeah, a gyro. That's a better way of saying it. Yep, that's exactly. Okay, so again, you could use discs if you wanted to. The problem with discs is you're going to have to do multiple, because you have two different functions, you're going to have to do two pieces. So I can actually do a cylinder and do it all in one integral. Okay, so the volume is going to be 2 pi, I have some integral, the radius, the height, and actually I'm going to leave a little extra room for the height this time. And again, we rotate it around the y-axis, so it's going to be dx. So this time the height, right, all of the other problems I did, the height started at 0 and went up to the function. This time the height is sitting between two functions, right? So anybody have any idea what I could do with those two functions to get the height, to get, you know, this part here, to figure out how tall this is? Okay, so you could add them, but the problem with adding them, right, is remember that this part down here is going to be negative. So if you just straight up add them, it's actually going to end up kind of, everything would cancel out and you would just get 0. Yeah, so you actually want to subtract them. So think about it kind of like if I had a line and I knew the top of the line is at 7 and the bottom of the line is at 3, right? You would do 7 minus 3 and go, oh, your line is 4 units long, right? So we're going to do the same thing. We're going to take the top function and we're going to subtract off the bottom function. So the top function is the 1 minus x over 2, and then we're going to subtract off the bottom function, which is x over 2 minus 1. And then the radius, right, is going in what direction here? Yeah, so the radius is going in the x direction. It's still just starting there at the x. And then my integral, right, my x's, I'm starting here at 0. But then what am I going to do to figure out where I'm going up to? Like, I want to go up to this point. How am I going to figure out what that point is? Yeah, set the two equations equal to each other. So we're going to have 1 minus x over 2 is equal to x over 2 minus 1. So if I move things, right, so I could have 1 plus 1 equals x over 2 plus x over 2. So 2 equals x. So that's 2. So we're going up here to 2. And so if I clean up that inside part a little bit, I have 2 pi, the integral from 0 to 2 of x times. So again, inside here I have a minus x over 2, and then I have a plus 1. So we're going to end up with 2 minus x dx, or 2 pi times the integral from 0 to 2 of 2x minus x squared dx. So 2 pi times 2x squared over 2 minus x cubed over 3, evaluated from 0 to 2. Could you do the subtractions before yeah, you could do the subtractions off on the side of your paper and then just put the 2 minus x in. I think, is that what you're asking me? Yeah, for sure. You can definitely do that. And so now if I plug in, I have 2 pi times, we have 2, well, so I should be a little, these guys would cancel, right? So this is just going to be 2 squared minus 2 cubed over 3 minus 0 squared minus 0 cubed over 3. So 2 pi times 4 minus 8/3 minus 0. So this is going to be 2 pi times 4 minus 8/3 is going to be 4/3. So the grand final answer is 8 pi over 3. Questions? No. Okay, then I have one more to show us. Does anybody need me to wait before I go to the next page? No? Oh. All right, so find the volume of the solid formed by revolving the region bounded by y equals x cubed plus x plus 1, y equals 1, and x equals 1 about the line x equals 2. So this one we're not going to rotate it about the x or the y axis. We're going to rotate it about something else. So what's going to happen here is we're going to have to adjust the radius. That's the only really big difference for the most part. So if I looked at the picture of what this looks like, so the line y equals 1 goes out this way. Here's 1. Here's the line x equals 1. It's going up this way. And this curve basically looks something like this. So we're talking about this kind of triangular sort of sailboat region. And then we're rotating it about this line, which is y equals 2. So we're going to have the same type region over here. So this has a big hollow part on the inside of it. So it's kind of like, trying to think what's the best way. I don't know. It's kind of like you have a volcano, but you like chopped off the top of the volcano and like cut a hole down the center of it. That's kind of what shape we're dealing with here. What do you mean, is it possible to do hollow cylinders? Like hollow, there's no ends on the cylinders? That's what we've been doing, but I just want to make sure I understand your question. Okay, that's fine. Okay, so that's my picture. That's not like my typical cylinder, right? So my typical cylinder sits, I'll stick one in. So here's like a typical cylinder. Okay, so in this problem, right, before I start sticking stuff in, we need to figure out what is the height, and then we also need to figure out what is the radius. So before I actually plug into my formula, let's figure these things out. So the height, right? If you look at the height, and again, I always want to go here on the side where it's shaded. So the top of the height is on what? Yeah, so the top of the height is sitting on that curve, the x cubed plus x plus 1, right? So the top height is going to be x cubed plus x plus 1. But then the height, just like in my last problem, it doesn't go all the way down to the axis. Where is the bottom of the height? Yeah, the bottom of the height is on 1. So the height is going to be the function then minus 1. So our height is going to end up being x cubed plus x. Now the radius, it starts at 2 and goes all the way out here, right? Are we okay with that is what the radius should be? Like in terms of the picture, right? The radius starts there at 2 and goes out to the edge. Yes, no. Okay. So so far, we've been measuring the radius starting at the 0 and going this way and saying, oh, that distance there we were calling x, right? So if that distance there we were calling x, and then I know that from here to here is 2, how much would be that pink radius? Almost, you're close. It's not quite x plus 2, right? X plus 2 would put me, if I took x and then I added 2 more, that would stick me out here, right? So, so the whole green distance is 2. I want to figure out the pink distance, so I need to subtract off the blue distance. So the radius is going to be 2 minus x. So that whole green distance is 2, and then I'm taking away that blue distance. So the radius is 2 minus x. So questions about the height or the radius? No. Okay, so then the volume is going to be 2 pi, the integral. So the radius, we said, is 2 minus x. The height is x cubed plus x. And then we rotated. So again, we didn't rotate around the y-axis, but we rotated around something that's parallel to the y-axis. So that's why we're doing dx. And then the limits of integration are always going to be, look at the original figure. So where does x in this original shaded figure, where does x go from? It goes from what's the x value over here on this side? Yeah, 0. And then it's going up to 1. So we're integrating from 0 to 1. So to be able to do this integration, we actually have to multiply those things out. So this is going to be 2 pi times the integral from 0 to 1 of 2x cubed plus 2x minus x to the fourth minus x squared dx. There's nothing I can put together, so we have 2 pi times 2x to the fourth over 4 plus 2x squared over 2 minus x to the fifth over 5 minus x cubed over 3 evaluated from 0 to 1. So we're going to have 2 pi times, if I plug in 1, I'm going to have 2 quarters plus 2 over 2 minus 1/5 minus 1/3. When I plug in 0, we would just get 0. And if you work this out, this ends up being 29 pi over 15. So 2/4 plus 1 minus 1/5 minus 1/3 ends up being 29 over 30, and then the 2 cancels and makes it 29 pi over 15. Questions? No. So that's the end of volumes. So we have one more application, well, kind of two. It's surface area and arc length, that we're going to do next class. So that's kind of the last part of these applications before then next week we're going to start series and sequences, the second part of the week. So I put up the homework for this was the section 9, so it says section 9.3 part 2, and then I had the 9.3 just regular homework up, and I will double check that is unlocked. So yeah, so there's 2 homeworks that you have due this week. Questions, or this upcoming week, I should say. No? All right.